This is the video on simple machines. So simple machines, they use energy. We remember energy is the capacity to do work. So we learned about the law of conservation of energy, which states that you cannot create or destroy energy. You can only change or transform it or transfer it to another object. So using that, we talked about work. Now, if work is done on an object, the energy of that object will change or transform. Something's happening to that energy of that object. And in order for work to be done, work is the scalar product of the force times the displacement times the cosine of the angle between those two. Basically, you're applying a force over that displacement or that distance, right? You're applying a force for a certain distance. Now, what are simple machines? So simple machines only help you do work. You cannot get any more work out of them than you put into them. So the work input equals the work output. This is for an ideal machine. Now there are 6, and I put technically 2 basic types of simple machines. You've got your lever, your wheel and axle, your pulley, and I say these are technically all types of levers because they do have a fulcrum. Inclined plane, wedge, and a screw, these are all technically inclined planes. So that's why I say there's 6. It's categorized into 6, but there's technically 2, right? Now, a simple machine can do 3 things, right? It can change the direction of your applied force. It can multiply your force at the expense of distance, and it can multiply your distance at the expense of force. So we've already looked at a ramp before, and a ramp is just an inclined plane. So what I want you to see is that if we look at this, right, you know the cart. I'm pulling the cart up to the same height. The same amount of work is done because it's going to have the same amount of gravitational potential energy at the top of the ramp. It doesn't matter how shallow or steep that is, even if it goes straight up, the work is the same. But notice what happens to the force, right? The force, the more shallow it is, the less force, but more displacement, right? So you're going to have to apply a lower force, more displacement though, right? So that's what ramps help us do, right? They help us apply less force. You're going to have to apply at a larger distance, but overall the force is what you're going to feel. And you can see that we did this lab earlier, the force and displacement, angle and ramp. If you multiply the force and displacement at every single point, you're going to get the same amount. And it's just the gravitational potential energy of whatever that object is at that height. Remember, and it doesn't matter what path you take, because remember, you're going up against gravity. Gravity is a conservative force. It is path independent. It does not matter what path you take up. It's the same amount of work, same amount of energy at the top. So that's what ramps allow us to do. Now, we also looked at a lever. Now, a lever is a simple machine consisting of a beam or a rigid rod pivoted at a fixed hinge, or a fulcrum. Now, there are 3 types of levers. We've got the first class lever, which the fulcrum is in the middle of the effort and the load. So an example is anything like a seesaw or something that's prying, scissors, pliers. These are all examples of a class 1 lever. Now, a second class lever, the load is in between the middle of the fulcrum and the effort. So this is an example would be the wheelbarrow, right? So you're lifting up with the wheelbarrow, and a wheelbarrow is a great example of one of those compound machines because the fulcrum is a wheel. So you've got 2 different simple machines there. Now, a third class lever, the effort is in the middle between the fulcrum and the load. So this is a special case because what this means is that, yeah, you're sacrifice you're getting more distance at the expense of that force. So example would be like you're uh, like a broom, right? So you grab the broom, the top is the fulcrum, you're moving the effort just a little bit, but you're getting a large distance on the end. It's the same thing the way like our arms work. Our biceps contract just a little bit, but your arm or your hand moves a large distance, right? So that's what a third class lever does. So in order to look at this, we did a lab, a fulcrum, and a place to stand. That's based on that famous quote. But what we did in this one, we looked at all 3 classes of levers and we measured like the force that it's required to lift the load off the table using these levers, and we changed the distance that the effort was from the fulcrum to see what happens. Now, what is the law of simple machines? So the law of simple machines simply states that the work you get in of a machine is equal to the work you get out of it. Now, we're looking at ideal machines. So for an ideal machine, the work input equals exactly the work output. So what this says is that at best, the amount of work you put into something is the amount of work you get out of something. You cannot get something for nothing, right? The output force is always the weight of the object being lifted, right? So if I'm lifting an object up, that's going to be, well, the output force. The output distance is the height at which the object is being raised. So you can see, yep, it's going to be being raised, and this is the equation: work out equals work in, and you just expand that out. The force out times the distance out equals the force in, the distance in, right? So you can see that equation here. So what is mechanical advantage? So in order to lift a heavy object up a given distance, you apply a smaller force, but through a longer distance. In each scenario, the same amount of work was done. Now, mechanical advantage is the ratio of input distance to output distance. So mechanical advantage basically tells you how much a machine will multiply your force. Mechanical advantage can be found by dividing the input distance divided by the output distance. So for a machine with no friction, mechanical advantage can also be found dividing by the output force by the input force. We're just going to use distance because we're going to get to efficiency in which the forces are a little bit messed up, but the distances will give you that mechanical advantage. So let's just do a problem, right? An ideal machine, ideal inclined plane. So an object with a mass of 6 kilograms is pushed up an ideal inclined plane, so that means no friction, for a displacement of 5 meters to a height of 2 meters. What force was applied to the object in pushing it up the inclined plane? How much work was done to the object lifting it to that height? What is the mechanical advantage of this simple machine? All right, so input force, right? So that's what we're looking for. If I'm pushing this object up, well, I just plug in everything that I know, right, into that equation. So 60 times 2, well, that has to equal, my output force has to equal, or my output work has to equal my input work, right? So I just solve it, and I'm going to get 24 newtons. So notice I'm applying a less of a force to get that up. Now, it says how much work was done to the object lifting it to that height. Well, it's going to be the output, 60 times 2, so 120 joules of energy, of gravitational potential energy. That's how much work. That's the input work, output work. Now I can calculate the mechanical advantage. So that's going to be the input distance, right, which is 5 divided by 2, the output distance, and the mechanical advantage is 2.5. So what this tells me is that for every newton that I put into this machine, I get 2.5 newtons back out, right? So that's what this is telling me. I'm going to have to apply it 2.5 times longer, but I do get that mechanical advantage. Now let's talk about efficiency. In real life, we encounter friction. Real machines must overcome energy losses due to friction. So for a real machine, work out does not equal work in. What this says is that we must always put in more work than when we get out. So no machine is 100% efficient in real life. Efficiency is a quantity to measure how much we get out of compared to how much we put in. Efficiency is a measure of how ideal our machine is. It tells us how much of our work is done is lost to friction, right? So how much of our energy is actually being used to lift that object? So let's take a look at a real inclined plane. So same thing. I'm lifting a 60 Newton object up a real inclined plane. Now, when we did ideal, that means no friction. We're not losing any energy. It was 30 newtons, right? 24 newtons. Now, I have to apply 30 newtons, right? So some of that energy is being lost to friction. So I'm going to do the same thing, and I plug these numbers in, right? So I am going to have a different output work and input work. So I just plug that in. I can calculate the mechanical advantage. Notice I still get 2.5 because that's the distance. That's not affected by the efficiency. But now let's calculate the efficiency. So my output work is just purely lifting that object straight up, right? Basically, it's gravitational potential energy, 60 newtons times 2, and you get 120 joules. Now, the input work is the work that you did going up the inclined plane. So 30 times 5, you get 150 joules. So some of that energy, the work that was put into this machine, goes to external forces. So it goes to like friction and heat, sound, like it's lost to the outside world. So you plug it into that equation and you get this machine is 80% efficient. That means 80% of the energy you put into this machine goes into lifting it. The rest lost to the outside world. So here's another question that we can ask. Well, is having a simple machine with a low efficiency necessarily a bad thing? So let's talk about efficiency again, right? If a machine is capable of doing some work in the reverse direction after the effort is removed, then a simple machine is known as a reversible machine. The condition for a machine to be reversible is that its efficiency should be more than 50%. A non-reversible machine has an efficiency less than 50%. That means the losses are more than 50%. This machine is what we call self-locking. The most common example is a screw. Now, a screw is not very efficient at all. I mean, very low efficiency. I mean, we're talking like 1, 2, 3%. And it's because you want it to lock. So what that means is if you think of like a lever, like a teeter-totter or like a wheelbarrow, you lift it up, you're the effort. If you remove the effort, it's going to go back. It's going to fall back down. But self-locking is a low efficiency machine like a screw. If you're using a drill to screw into the wall, you don't want it to reverse, right? You want it to stay where it is. So that's why it's very low efficiency. Same thing with like a car jack, which is another kind of a screw, or like an axe where you hit some wood. Well, it can stick in there, right? It doesn't necessarily just pop right out. And an inclined plane can be very low efficiency if the friction is high enough and maybe the inclined plane is low enough, because sometimes things can just sit on an inclined plane without sliding back down. So there is such a thing as having, sometimes you want a low efficiency on a machine. So just as a final thought, remember there's too much unknown in the universe to take a break from learning. Get out there and question everything.